Hello and welcome to topic 4. In this topic we discuss something called derivatives, which is the main tool in calculus that we'll be learning and applying in this course. So let's go ahead and start with the objectives. Alright, so let's start by talking about our objectives for this particular topic. We will be discussing the instantaneous rate of change, which we saw in topic 3, how that's related to the tool that we call derivatives in calculus. We will be talking about different rules for derivatives and how to find derivatives, including rules for constant functions, linear functions, and polynomial functions. We'll also do a special rule called the product rule, and we will relate that to the demand function and to marginal demand. We'll also talk about how to evaluate and interpret derivatives, so finding values of derivatives and then making sure we understand what those numbers mean. And finally, we will have a more thorough discussion of marginal analysis, which we began in topic 3, I believe, when we talked about marginal revenue and marginal cost and marginal profit. We'll now do this in a little bit more detail. So those are the objectives for this topic, so let's go ahead and get started. So to motivate some of our discussions here, we're going to start by looking at the revenue function. And eventually, we want to talk about the marginal revenue. But first, let's start by just looking at a revenue function. This is a function that we've seen before. Remember that on the horizontal axis, you have quantity of items sold, and on the vertical axis, you have total dollars in revenue that come from selling that number of items. Keep in mind that we have the revenue function, so that means that the graph goes through the origin, 0, 0. That makes sense if you recall, because if you sell Q equals 0 units, then you have 0 revenue. So that point is on the curve. So that's the function we're going to be exploring. Let's take a look at what we want to do in particular on the next slide. This particular question should be familiar to you. We've talked about it in topic 3 and a little bit in topic 2, but mainly topic 3 when we talked about how fast some function was changing at some point. And so when we want to ask the question, how fast is the revenue changing when 20 units have been sold, or at this point that you see here on the curve, we're really asking the question, how do we measure the marginal revenue at Q equals 20 units or 20 items sold? So that's the question in front of us. Is we have a point that we pick that we are interested in, and we want to know exactly how fast that function, in this case, how fast is the revenue changing at that particular moment. So that's the kind of question that derivatives help us to answer, but a lot more efficiently and a lot more accurately than what we saw with the estimating techniques in topic 3. Now, as we saw in topic 3, the instantaneous rate of change is a measurement of the slope of the tangent line at a particular point, in this case when Q equals 20. So we pick that point and then we draw a tangent line and then we try to measure the exact slope of that line. And we saw in topic 3 that can be problematic because we only have one point, and to do a slope calculation you need 2 points. So calculus is going to get around that limitation for us and allow us to do that slope calculation very easily, as we'll see in the next few slides. So formally, we introduced the tool called the derivative. In calculus, this is the tool that we use to measure the exact slope of a line that is tangent to a given point. So as I mentioned before, this is more accurate and more efficient than what we saw in topic 3 with the estimating methods. Remember, we had the forwards-backwards method that required us to use 2 points. We also had the forwards-only method, which also required us to use 2 points. Now, from this point forward, when we talk about marginal change or calculating the slope of a line at a point or the instantaneous rate of change, we will now, from now on, use this formal tool called the derivative. So at this point, from this point on in the quarter, whenever you see the word rate instantaneous rate of change or marginal change, you want to think derivatives and calculus. So before we begin listing the rules and explaining the rules for finding derivatives of functions, let's talk about some notation. So let's start with the general function notation y equals f of x. So y is a function of x. If y is a function of x, then the derivative is denoted in a variety of different ways, as you can see here in the middle of this slide. The first one is, the way we say this is y prime. So that little dash there is red prime. So y prime is the derivative of y. We also have this other notation where we take the function f and we put a little prime symbol there. And so we have f prime of x. So that is how we read that notation, f prime of x. So when you see that little apostrophe, that little dash, that tells you that you no longer have the original function in front of you. You have the derivative function. So notice that the derivative itself is a function. F prime, the derivative, depends on x. So both the original function f and its derivative are functions. And in fact, that's how derivative got its name in history. Mathematicians said, okay, we'll start with a function f, and from that function, let's derive another function that tells us how the original one is changing. So derivative has that history behind it, the word. The last notation here is read dy dx. Very simple, dy dx, not dy over dx or dy divided by dx. We just say dy dx. Now you have to be a little bit careful here because it looks like division, but it's not. Some students, when they first see this notation, think that, well, we're dividing the derivative of y by the derivative of x. And that is not a correct interpretation. What this is saying on the top is I'm taking the rate of change of y, and then on the bottom, with respect to x. So a derivative tells you how the y-coordinate is changing, how fast the y-coordinate is changing as you allow the x-coordinate to change. So this is the reason for this notation, and the reason why we say what we do. Dy dx means the rate of change of y with respect to x. Now the most common one that we're going to use in this class is the prime notation. We'll either use the y primed or the f prime of x notation. And we will, for the most part, not see much of the dy dx notation. It's just a little bit too cumbersome for this course, but it is out there, so be aware of it. Here's a little bit more notation that we'll be using here in this particular course. In a business calculus setting, we will adopt new notation for marginal functions. So as you can see here, marginal cost, marginal revenue, and marginal profit can be denoted in a couple of ways. We can use the traditional notation with the primes on the right. So we can talk about C prime of Q, which is the derivative of the cost function. That function tells me how fast the costs of production are changing as my quantity produced increases. So we can use C primed of Q, or we can just say MC for marginal cost. So remember, we're defining the marginal cost to be measured by the derivative, so that's the reason for this notation. This MC and MR and MP notation is a little more common in business and economics books as opposed to math books. Math books tend to stick pretty strictly to the prime or the dy dx notation that we saw in the previous slide. So marginal cost can be written as MC of Q, marginal revenue MR, and so on. So we will use these interchangeably throughout this quarter.